All right, today we're going to talk about the bipolar junction transistor. Shown in the figure here is the cross-section of a BJT or bipolar junction transistor, and you can see that it typically has a vertical construction where the collector is at the lowest layer, the base is between the collector and the top layer, the emitter. You can see that the cross-section is formed by this rectangular box. And typically, we draw this vertical cross-section like the figure that I'm pointing to right now. You can see that the emitter is doped heavily with an N-type material, so I've noted it as N++. The base is a P-type material that's doped slightly less heavily, and the collector is doped even less heavily. However, the ohmic contact to the collector is doped as N++ in order to make sure that it makes a good contact to the N-type region. If we look at the cross-section of the BJT, you can see that there are P-N junctions. These are back-to-back P-N junctions. So we effectively have two diodes. And the diode that controls the operation of the BJT is the base-to-emitter diode, or the base-emitter pair. We can also make a PNP transistor. You can see that the structure is also a vertical structure. We just changed the type of doping that we're using. So the emitter is a heavily doped P-type material, and the collector is a lightly doped P-type material, and the base is a slightly more heavily doped N-type material. And again, we have back-to-back diodes. If we look, we can define the regions of operation of the BJT by the voltages that control them. Here we describe the voltages between the collector and base and emitter. So we have the collector to base voltage, VCB, and the base to emitter voltage, VBE. For the PNP, we reverse the subscripts, and then the operation is described similarly. So we have VEB, the emitter to base junction, and VBC. We label the junctions CBJ, EBJ, these are the collector to base junction and emitter to base junction respectively, and of course we have the same things on the PNP transistor. We have schematic symbols for the transistors. The schematic symbols for the transistors are shown here. The NPN has an arrow in the positive direction between the base and emitter. This symbolizes the direction of current. Direction of current in the forward active region should generally be flowing from the collector to the emitter and from the base to the emitter. For a PNP transistor, it's exactly the opposite. So the arrow direction is reversed, and current should be flowing from the emitter to the collector and generally from the emitter into the base. The regions of operation of the transistor are dictated by the biasing of the PN junctions. So we have FB for forward biased and RB for reverse biased. We have four combinations that we can possibly achieve for the emitter to base and collector to base junctions. So if the emitter to base and collector to base junctions are both reverse biased, we have cutoff. If both of the junctions are forward biased, then we have saturation. If the emitter to base junction is forward biased and the collector to base junction is reverse biased, then we have the forward active region. And finally, if the emitter to base junction is reverse biased and the collector to base junction is forward biased, we have a reverse active region. And we can note in cutoff, this means that no current flows. We use this mode for switching. In saturation, it behaves like a voltage-dependent resistor, so a resistor that has a function of voltage. In the forward active region, it behaves like a good amplifier. And in reverse active, it behaves like a bad amplifier. Now we're going to get into the details of why that is, but ultimately the more heavily doped emitter region works better as a source of electrons in the NPN transistor than the more lightly doped collector region, and that causes this behavior. All right, so with that, we will stop here and go on to the next lecture